So we want to know, when we look at those real numbers that Mendel had, when he had a ratio of 3.16 to 1 or 2.92 to 1, is that close enough to 3 to 1? Or is something else going on? And so just as we could use a t-test to see if there's a statistically significant difference between two groups, two means, we can use a chi-squared test to see if there's a statistically significant difference between two ratios. And so we would use that to compare our real data that we collected by growing our pea plants to the ratio we expected, to say, is that close enough to 3 to 1? Or is it not really 3 to 1? And even though it looks like it might be, it's not. And maybe things aren't quite the way I thought they were. So we use it to compare our observed ratio to our hypothesized ratio. And here's our way to think about how a chi-squared test works. When we flip a coin, we expect to get heads 50% of the time and tails 50% of the time, right? That's how coins work. That doesn't mean we're going to get heads first and then tails and go back and forth perfectly, right? We know that it might not be perfectly 50-50. We're comfortable with that idea. But then if you flip a coin and get 63 heads and 37 tails, that seems really different. If it were, 55 and 45, I'd be comfortable with that. But 63 and 37, that seems like it might be pretty different from 50-50. That might be more like 2 to 3, right? It seems like something different's going on. So a chi-squared test will let us compare our 63 to 37 to 50-50 and tell us, is that similar enough to 50-50 that it's still 50-50, or did somebody give you a trick coin, which you can get those at magic shops and places, that a coin that will show up heads more often than tails and things like that. The way we use it in biology is to compare the outcome of a trial cross, like we just talked about, to our predicted results to see if that number of purple and white pea plants we got is enough like 50-50 for it to count, or is something else going on? If your ratio is statistically significantly different from the expected ratio, it might be there's a problem with your genetic understanding. You might have thought that this was a simple recessive trait like we just talked about, when actually there's some more complicated stuff going on in how the trait is inherited. Or it might be that you were wrong about the genotypes of the parents of the cross. So if you're doing a test cross like Mendel's was, and you get something other than 100% purple or 50-50 purple and white, then you were wrong about what you thought you were doing, and you did some other cross besides the one that you expected to be doing. And so that's how biologists use the chi-squared test, is to compare actual genetics results to that hypothesis we came up with based on the principle of segregation, or whatever other principles we are using. So imagine that you perform a monohybrid cross, just one trait, between two corn plants. One has purple grains and one has yellow grains. So the cool thing about corn is every grain of corn is a separate biological individual with its own DNA, its own genetics. It's a separate cross between the two parents. And so one ear of corn contains hundreds of different crosses between the two parents. And so when you're looking at a piece of corn that's entirely purple, you're looking at a cross that resulted in nothing but purple offspring. If you're looking at one that's entirely yellow, you're looking at a cross that resulted in nothing but yellow offspring. So when we cross our purple corn with our yellow corn, in our F1 generation, all the corn have purple grains. We're going to hypothesize that this is an example of complete dominance, where purple is the dominant trait. It works just like we're expecting it to. So if we cross a true breeding purple parent with a true breeding yellow parent, and the F1 generation is all purple, what would we expect the F2 generation to look like when we cross everybody with each other randomly? What ratio would Mendel expect? 3 to 1, yeah, 3 purple, one yellow. That's what we would expect. Oh, and there's that question again. We just answered that question. So when we actually do it, we observe 745 purple grains and we observe 275 yellow grains. And if we were in the lab today, you would have actual ears of corn and you would actually be counting out grains just like that. So 745 to 275, that adds up to a total of 1,020 grains. Our hypothesis was a 3-to-1 ratio. So 3-to-1 ratio is the same as 3/4 to 1/4 or 0.75 to 0.25. So you can see we added 3 plus 1 to get the denominator here. So it's 3 out of 4 over and 1 out of 4, or 3/4 and 1/4, or 0.75 and 0.25. If we want to determine the expected number if our corn was exactly 3-to-1, we're going to multiply our total number, 1,020 grains, by that ratio, our 3-to-1 ratio. So the expected number of purple grains would be 1,020, our total observed, times 0.75, our expected ratio, or 765 purple grains. The expected yellow grains would be 1,020, our total, times 0.25, our expected ratio, oops, there's a typo, and that's going to be 255 yellow grains. So what we're asking is, we got a ratio of 745 to 275. Is that close enough to 765 to 255 that we would say it's a 3-to-1 ratio? Or is that too different? And we haven't quite figured out corn genetics yet. To test that, we're going to use a chi-squared test. Up here, you can see the equation for the chi-squared test. The chi-squared test considers the difference between the observed number and the expected number for each category, each phenotype in this case, and divides it by the expected number, and then squares that, and then adds up all of those squares. The good news for you is that you don't have to do that by hand. We have a nice table to help you out. Also, this sort of looks like a curvy X with a 2. That's chi, the Greek letter chi squared, and that's our test statistic. If you remember in the t-test, our test statistic was called t. In the chi-squared test, it's called chi-squared. And that, because our statistic is called chi-squared, that means you do not need to take a square root of it because the value you want is called chi-squared. So instead of you having to work through this formula by hand or in your calculator, we have a nice table to help you out. Oh, and that was supposed to, so I'll walk you through it. Here are our observed data. So we saw 745 purple and 275 yellow for a total of 1,020 corn grains. We would expect 1,020 times 0.75, 3/4 of them to be purple. We would expect 1,020 times 0.25, or 1/4 of them, to be yellow. And again, our total stays 1,020. To calculate this, we're then going to do observed minus expected. Oops. And that's what this column is. It's observed minus expected. So 745 minus 765 is minus 20. 275 minus 255 is 20. Our next column, we're then going to square it. So we're going to take this number and we're going to square it. Minus 20 squared is 400. Positive 20 squared is also 400. And then our last column, we're going to take our square and divide it by the expected. So 400 divided by 765 gives us 0.52. And 400 divided by 255 gives us 1.78. And then the last step to get our chi-squared value is to add up those squares. So 0.52 plus 1.78 is 2.3. Our chi-squared value equals 2.3. And that's how you calculate your chi-squared value. Then you're going to go to your chi-squared table, just like you went to your t-table before. The chi-squared table is on the last page of your lab, and you're going to look up your chi-squared value in that table to find the p-value for that chi-squared value. For chi-squared test that we're doing, the degrees of freedom this time is the number of phenotypes minus 1. So how many phenotypes do we have?
2.
2, purple and yellow, right? So our degrees of freedom will be 2 minus 1. Our degrees of freedom will be 1. So with a chi-squared of 2.3 and the degrees of freedom of 1, we're going to jump over and look at the chi-squared table. So here's our chi-squared table. Our degrees of freedom are 1, so we're in this very first column, and we're looking for 2.3. It's getting higher, it's getting higher. Here we are. So 2.3 would be between 1.32 and 2.70. So then we go up to the top row. Our p-value is going to be between 0.25 and 0.1. Both of those are greater than 0.05. So we're on this side of the table, and that means we accept our ratio hypothesis. What was our ratio hypothesis for this test?
Wasn't it 3 to 1?
It was that they were in a ratio of 3 to 1. So we have accepted they are indeed in a ratio of 3 to 1. So then, oh, there they are. So our degrees of freedom was 1. Oh, that's pretty. Our chi-squared value was 2.3. Our p-value was, we don't know for sure, but it was greater than 0.1. And so we can conclude that we accept the 3 to 1 ratio. Therefore, these plants were in the ratio of 3 to 1. The purple parent must be true breeding and the yellow parent must be true breeding. We are comfortable with our hypothesis as we worked it out.